Welcome to the Explainer. Today, we are diving into a really cool puzzle. It's all about how you can get the absolute biggest result out of a single powerful move. We're going to break this whole thing down step by step. Okay, let's jump right in with a challenge. Take a look at this list of numbers: 3, 2, 1, 4. Here's the deal. You get to reverse any single chunk of this list. Just one reversal, that's it. Your mission is to make the new list as big as possible. So, what's the move?
All right, before we can solve anything, we need to make sure we're all on the same page. We've got to understand the rules of the game, which really means knowing what kind of list this is and what bigger actually means here.
First off, the technical term for what we're working with is a permutation. Now, don't let the fancy word fool you. It's just a way of saying it's a list where every number from 1 up to n shows up exactly one time. No repeats, no skipping numbers. That's all it is. So, how do we decide if one list is bigger than another? Well, we use this idea called lexicographically greater. It sounds super technical, but honestly, the best way to think about it is like looking up words in a dictionary. You just compare them from left to right, one spot at a time. Let's see it in action. It's pretty simple. We compare the first numbers, 4 and 4. They're the same, so we move on. Second numbers, 3 and 3, still the same. But, boom! At the third spot, we hit a difference. Array A has a 2, and Array B has a 1. Since 2 is bigger than 1, we stop right there. Array A is our winner. It's lexicographically greater. Okay, so now we get the rules. What's your gut feeling on how to solve our puzzle? I bet most of us would probably come up with the same, pretty straightforward idea. The most obvious strategy seems to be, hey, just find the biggest number in the entire list and then do whatever reversal it takes to get that number into the very first spot. I mean, a bigger number at the front almost always means a bigger list overall, right? Makes sense. And if we try this on our original puzzle, 3, 2, 1, 4, it seems to work like a charm. The biggest number is 4. If we just reverse the whole thing, we get 4, 1, 2, 3. The 4 is now at the front, and yeah, that's a much bigger result. Feels like we nailed it. But here's where things get interesting. Does this nice, simple strategy always work? What happens if we come across a case where the biggest number is already right where our strategy wants to put it? Take a look at this one, 3, 1, 2. The maximum number, 3, is already at the front. So our simple strategy would tell us to do nothing. It leaves the array exactly as is. But is 3, 1, 2 really the best we can do here? The fact that our first idea failed is actually a good thing. It leads us to a much smarter insight, a real aha moment that's going to unlock this whole puzzle for us. You see, the secret isn't to just look at the array we have. The real trick is to create a benchmark. Think of it as the perfect, ideal, absolute best-case scenario version of that array. And how do we make it? Easy. We just sort the numbers from biggest to smallest. So here it is, our problem array, 3, 1, 2, sitting right next to its perfect benchmark, 3, 2, 1. This side-by-side view is everything. It tells us not just that our array could be better, but it shows us exactly where the problem is. So, using this benchmark idea, we can now lay out a simple 4-step process that's basically guaranteed to work every single time, no matter what permutation you give it. All right, here's the game plan. Step 1, make the benchmark by sorting in reverse. Step 2, compare your array to the benchmark, left to right, and stop at the very first place they don't match. Step 3, figure out what number should be there, that's your target, and then find where it is in your current array. And finally, step 4, just reverse the chunk of your array that's between the mismatch spot and where you found your target. Okay, that might sound a little abstract, so let's put it to the test. We're going to use that tricky case from before, 3, 1, 2, and see how this new strategy just completely cracks it wide open. So let's do the comparison. At index 0, we've got a 3 in our input and a 3 in the benchmark. Perfect match. We keep going. But at index 1, we hit it. Our input has a 1, but the benchmark tells us a 2 is supposed to be there. That's our starting point right there. So our mismatch is at index 1. That's where our reversal is going to start. And the number we're trying to move into that spot is the number 2, the one from our benchmark. All right, next up, we have to find that target value, the number 2, inside our original array. We just scan across, and there it is. It's sitting at index 2. That's going to be the end of our reversal. And now for the actual move.
We just take that little slice of the array between our starting point, index 1, and our endpoint, index 2. That little piece is just 1, 2. And all we do is flip it. And there you have it. The 1 and 2 swap places, and our final result is 3, 2, 1. And this isn't just a better answer. It is the absolute 100% lexicographically biggest version we could have possibly made with just one move. Our strategy worked perfectly.
So what's the big lesson here? The simple idea of just grabbing the biggest number was a trap. It was too simple. The real, powerful solution came from defining what a perfect outcome looked like, our benchmark, and then finding the very first place where our array strayed from that path. Fixing the earliest mistake gives you the biggest reward.
And this kind of leaves us with a final thought, doesn't it? This whole technique of comparing where you are now to a perfect benchmark, that's not just for weird coding puzzles. Where else could you use this? In project planning, building a new habit, even fixing something that's broken. How many other tough problems could be made way simpler if you just started by imagining the perfect outcome?